All right, we're going to try a new method of video lessons with our bond polarity and electronegativity lesson. I have a document camera, hello, that I can use. I'm not sure if it's going to be great because it has a little bit of a delay on it. Like I put my hand here and I'm wiggling my fingers and it takes a while for you to see that. So we'll see. But we'll try it for this one and see how it goes. So this lesson is about, as you can see up here, bond polarity. We are also going to be talking about molecular polarity. So the difference is that bond polarity refers to a bond, whereas molecular polarity is going to refer to an entire molecule. And we're going to revisit the idea of electronegativity, which was a concept that you learned last year in honors chemistry. So first of all, just a quick little reminder that a covalent bond is talking about the sharing of electrons. So when we hear this word covalent, we are thinking, oh, sharing of electrons. But in actuality, the sharing is not necessarily equal. That pair of electrons may be equally being shared between your two atoms, but a lot of times one of the nuclei is actually hawking the electrons. And that's where we get the difference between what we call a nonpolar and a polar covalent bond. Nonpolar is where there will be equal sharing going on. And if you take a look at this little image that I have here, you can see that the electrons are right smack dab in the middle of these two fluorines, indicating that they are equally sharing those electrons. I'll often use my husband and I as an example. I like to say that we equally share our children. So you can think of those two little electrons as our children. And because they're being equally shared, you can envision them sort of positioned halfway in between. Now, really, we know electrons are buzzing around all around the place, but it's being equally shared. So each nuclei is getting the effect of those those electrons equally. If the element is the same, then the sharing will be equal for sure. Okay, if the element is the same, then the sharing will be equal for sure. What we actually use to determine whether or not our bond is polar or not, and again, this one we know is nonpolar because the atoms are the same, but we will end up using numbers. And the numbers we're going to use are these electronegativity values. So this table here is a table of what we call electronegativity. Let's jump down to that just for a second. We'll go back up to those examples up top. As you can see here, it says that electronegativity is what allows us to predict whether or not a bond will be either ionic, polar covalent, or nonpolar covalent. Now we can pick out the ionic ones pretty easily. We know our ionic compounds are our metals with a nonmetal, or nonmetals. But in terms of polar covalent and nonpolar covalent, they're both sharing. So we have to learn how to tell the difference and how to decide which ones will be polar and which ones will be nonpolar. So electronegativity, a review from last year, is the ability of an atom to attract electrons to itself. It's not a measure of energy, okay? It's an arbitrary number that they came up with, and it's representing how likely an electron is to be attracted to the nucleus of something. The substance with the highest electronegativity, and you might want to box this one in here, is fluorine. Fluorine has the highest electronegativity, and they gave it the value of 4, 4.0. I have no idea why. Please don't ask, because I really don't know. But they made it 4.0, and then all the other ones are relative to it. So you can see oxygen is at 3.5. So fluorine does it better, but oxygen does a pretty good job of attracting electrons to itself. And then you can kind of see over here, not a very good attracting in an electron, because we know all of these guys want to lose an electron. So higher electronegativities over here than over here. Okay, and that trend is pretty true to our ideas that we already are understanding. So if you look up fluorine's value, you can see, if we go back to this problem up here, that fluorine has a value of 4.0, and the other fluorine is also going to be 4.0. So think of that number as how hard it's pulling. If this fluorine is pulling at 4.0 and this one's pulling at 4.0, net, you're going to cancel out. Their difference is 0. And so that force of pulling is going to be equal. So if Mr. Corman is pulling on our children and I'm pulling on our children and we're both pulling equally as hard, you're going to have the exact same force, hence canceling it out. And that's what makes it nonpolar. Okay? If you have an uneven pulling going on, you're going to end up with a polar molecule. And that's what this next example is. If we look up fluorine down here, we have a 4.0, as we said, was the electronegativity of fluorine. Hydrogen over here is only at 2.1. So think of fluorine as hogging those electrons, really pulling them in close to it. And hydrogen is trying to take them, but only at a rate or a power of 2.1 compared to 4.0. So you can see I drew the electrons on this one much closer to the fluorine than the hydrogen. Now, are they still being shared? Absolutely, but they're being unevenly shared. So this bond up here we call a nonpolar covalent because it's being shared. This one, there's unequal sharing, so it will be a polar covalent. And that's what we're going to use. We're going to use these electronegativities to decide whether or not individual bonds are polar or not. Now, we will take this into molecular polarity soon, but this is just about literally our electrons that are between two atoms. So down here again, you have your electronegativity table. I will give that to you on tests and quizzes where applicable, but it's not something you need to memorize, so please don't think that you have to. You will have it as reference when needed. All right, go ahead and flip your notes over to the other side. The polar one we were looking at before, the HF, I've drawn it again here on your paper, representing it the two ways that we can represent polar bonds. If you want to put a star next to number 1, that's actually the more common way that we will show polar bonds, okay, and the way we draw a polar bond. Instead of just drawing it and saying it's polar, we actually will use this notation most often. So the notation consists of doing an arrow, okay, an arrow, and then on this side there's like a little line going down. Essentially what's happening is it's making kind of a plus sign over on one side, and then the tip of the arrow is over here. Now the way you decide where to put the tip of the arrow versus this plus sign that we have here is based on the electronegativity. So we knew that this one was 4.0, we knew that this one 2.1, so we'd already decided that this bond was polar. So we're going to represent that polar bond with this this symbol. Okay, the tip of the arrow always goes with the more electronegative one. So you might want to write that down. Tip with more electronegative atom. Okay, like so. There's a second way shown here, and that makes use of this symbol. It looks kind of like a figure 8 that you don't quite finish with a plus, and the same one but with a minus. And regardless of which one you're looking at, the reason why here this is supposed to be indicating that this side is kind of negative and that this side is positive, and then you can see the negative and the positive actually written on the second one. And so what it's really doing is it's telling us that one side of the molecule has the electrons more. So it's going to be kind of negative and kind of positive. I say kind of because it's still sharing. It's not an ionic bond. But what you can do is think of this symbol right here means partial. So it's saying that this is a partially negative side, and this is the partially positive side. Okay, and that's what polarity means unequal. And so if it's unequal, then there's going to be a little bit of unevenness to the positive and the negative. Now, to figure out whether or not something's polar or not, as we did before, we looked at these two values and we said that they were different. It's not quite as simple as just saying they're different. We actually need to always do subtraction. We need to subtract those two electronegativities. So for this one, if we subtract 4.0 minus 2.1, we get 1.9. Then you're going to go down here, and you do need to learn this. Okay, you do need to learn these values. So write yourself a little note to learn these. If your difference, okay, so when you subtracted them, if your difference is 0.4 or less, then it is considered even sharing of the electrons. Even if there's a little difference, it's still considered even sharing, and it will be non-polar. If the difference is somewhere between 0.4 and 2, so between 0.4 but less than 2, it will be polar covalent, which is uneven sharing of those electrons. And if it's greater than 2, then that means it was actually ionic. You'll get those types of ionic ones greater than 2 when you mix a metal and a non-metal, because remember those metals had really low electronegativities and the non-metals were much, much higher. So for now, because this will get more intense as we start doing molecular polarity, for now this is what you're going to be doing. You're going to be looking at individual bonds. So I've shown them as lines here instead of 2 electrons, but it's the same thing. So it's asking you to decide, is this bond right here between these 2 atoms polar or non-polar? So what you're going to do is you're going to look up your electronegativities. You might have to flip back and forth a little bit. So you're going to look up your electronegativity. You'll start with this one. Well, I guess we should read the question. It says, for each of the following sets of bonded pairs, determine which pair is more polar and place the arrow over the bonds to indicate polarity. So if you look at boron, boron's value is 2.0. And iodine, if we look at iodine on there, its value is 2.5. So we want to subtract those two. Always big one minus small one. So the difference for boron and iodine is 0.5. Boron here, of course, will still be 2.0. Chlorine is 3.0. So if we subtract those two, we end up with a difference of 1.0. So both of these bonds are polar. The reason I know that is look at your differences. The difference of 0.5 and the difference of 1.0 both fall into the category here of polar covalent. So both of these are polar. I'm not going to write on my paper that they're polar. The way I'm going to show that they're polar is by using that arrow. Okay. Now we want to put the tip of the arrow over the more electronegative one. So I'm going to draw the arrow pointing to the right. Okay, pointing to the right. On this one, the more electronegative one, again, is the one on the right, which is just a coincidence. But there was also another part to this question, and it said which one is more polar. Which one do you think will end up being more polar? Do you think it's based just on their actual electronegativities or in the difference in the electronegativity? The answer is the difference in the electronegativity. So because this one is a larger difference, it means it's more polar. Means chlorine hogs the electrons worse than iodine does from boron. So larger difference means more polar. So let's try another one. So if we look up Si on your table, you should find that it's 1.8. If you look up oxygen, it's 3.5. Subtract those two. This is usually how I show my work. You're welcome to do it a different way if you'd like, and I do need to see the work for these. Then you get 1.7. Okay, so that one is polar. Falls into the range here of 0.4 but less than 2. So I'm going to draw an arrow, tip of the arrow over the more electronegative element. So again, it points to the right. Now this one, you can tell right away that it's going to be nonpolar. So I don't want to put any marks on it at all. No arrows because it is nonpolar. The arrows are used only for polar. If you want to write down the values so that you have them, that's fine. But you know that no matter what the value was when you subtracted them, they were going to cancel away. So that one is, so it asked which one was going to be, I guess up here I should probably, I don't know how I want to do this, box in my answer, like so. And then on this one, my answer will be this one. Okay? And remember, you got to put those arrows if they are polar. Now, I left this one on here intentionally to show you there's double bonds there. Double bonds do not affect this at all. This has to do with how well the nucleus wants, or how much that nucleus wants those electrons, okay? The ability of that nucleus to attract the electrons. It doesn't matter how many there are, the nucleus attracts regardless of the number of them. So it doesn't matter if it's a double bond, you're still going to do it exactly the same way. So 2.5, and then oxygen is 3.5, so we get a difference of 1.0, which does make this thing polar. Tip of the arrow goes over the more electronegative. Sorry, I'm running out of space there. Notice all my arrows were pointing to the right. Please don't just assume that to be the case, just as a coincidence. And then carbon is 2.5. And if you look at sulfur, you're going to find that it's also 2.5. So even though they're different elements, they have the same ability to attract electrons to their nucleus, which means their electronegativity difference is 0. So just like this one was nonpolar, so is this one. So if they're asking us which one is more polar, it's not the nonpolar one. You know that it's going to be the polar one. So it looks something like that. So your homework tonight is going to have some problems that look like this. Now ultimately, one bond's polarity is not that important to us, but you have to be able to do this to be able to do the molecular polarity. That's what we'll move into next.